Good evening. Przepraszam, że nie mówię po polsku. Na tyle dobrze, żeby wygłosić tę prezentację, ale mieszkałem w Polsce trochę. The rest of it will be in English. All right, so my name is Andrus. Thanks for the introduction. And tonight we're going to be talking about Java data processing in a specific way to work with data in Java with data frames. A few words about myself. I'm a founder of this company called Object-Style. Actually, our biggest office is in Warsaw, here on Marszałkowska, 10 minutes away from here. We have people who program in different technologies across the spectrum, you name it. But I myself, and when I started this company, I was a Java developer as a programmer. I still write a lot of Java code. It's all out there on GitHub. I participate in a number of open source projects. As you can see here, the 4 of them. The first one is Apache Cayenne. This is kind of this is an ORM similar to Hibernate, but we solve the same problem in a different way of object relational mapping. And this is this was the first project where I got involved, and it started it all for me, and eventually became a part of the Apache Software Foundation. The second project is Boutique, and Boutique, it can be described, it's an environment to like start your Java applications, to write your Java applications. It's kind of like, again, like Spring Boot, like to give analogies that everybody is familiar with, but it is much more lightweight, so it's not programming to annotations, it's programming with objects essentially, and it's much faster, smaller. The startup times are awesome, so you can restart your applications quickly. So essentially, it's just this very lightweight and nice Java environment where you can build applications from very small ones to like very large ones with lots of modularity and so on. The third project is Agrest, and I'm originally from Belarus, so the word Agrest is the same in Poland and in Belarusian. It means, you know, the berry. That's displayed there, but of course it also rhymes with REST, so it has something to do with web services. And how many of you are familiar with GraphQL? Yeah, quite a few people. So essentially the idea is the same, and the idea of Agrest and GraphQL is that when you write in a web service, you're not limiting your consumer to like a fixed data structure that they can consume, they can request, but instead you're providing an access to a graph, and they can get just a few properties of that graph from some root, or they can actually drill down and resolve relationships and like get like the entire tree of objects in one call. So this optimizes the consumer a lot and just makes, you know, the job of data aggregation, it just moves it to the back end. And but at the same time, while GraphQL does it, they invented their own protocol for it. We decided to stay within the space of just normal REST, so just it works using all the HTTP primitives like methods, you know, get, post, put, delete, so on, query parameters, and you can also navigate the graphs. And it has an Apache Cayenne backend. Backends are pluggable, but like the main backend is Apache Cayenne. So essentially, you can turn your database into a graph served by a REST service like very easily. And the last one is DFLib, but we're going to be talking about it today, so I'm not going to do a special introduction there. And instead, we're just going to talk about Java data processing. So if you ask a Java developer, is Java a good choice for data processing? I guess the answer is usually, yeah, sure, why not? But the industry as a whole probably has a different opinion. So if you look at the what people are using for data processing, Java is probably, I don't know, it's not close to the top. So you would start with like Python and other similar technologies, maybe Scala for Spark and stuff like that. So Java is somewhere out there, and I'm trying to, as a Java developer, I was always like, okay, why? So like, yeah, I used Pandas myself and like was trying to do some data work in Python. And I like Java much more, and but it was missing like some critical components. And in this presentation, I will try to show essentially the main components that I think if we plug those holes, we can be just as productive with data work as any Python programmer is. So first, let's look how we represent data in Java typically. So normally we would, of course, Java is an object-oriented language, but what do we, like, how do we structure our objects is what's important. And of course, the default approach is that we create an object with some properties that contain some data values. Like for instance, here I have a product, and it's a record, but a record is also a class. And it has name, color, and price properties. And this is how we typically model our data objects. So we would create fields that correspond to some simple values. And then if we have a lot of them, we put them in collections. So we put them in lists, maps, sets, and so on. Right? Then if we need to interact with an environment where data is modeled in a different way, for instance, with a database, where data is modeled as tables with some relationships. There are great tools like Hibernate and Cayenne and so on that allow us to do this mapping and sort of not think about it twice. Well, of course, there's lots of complaints about ORM being too complex and cumbersome and everything, but I think they're missing one point, that ORM is great for this kind of one-to-one correspondence when your object model corresponds very closely to your database model, and your structure of your data doesn't change. The ORM is great, so you can read objects from the database, you can write objects to the database, but you can't step outside the boundaries of that normalized model, essentially. And this is and so when I'm talking about data processing, I usually mean data transformation. So it's this is when we are not just reading from the database, writing to the database, but we're actually changing our data. We're changing the structure of our data. And in Java, the standard way of doing that is, of course, Java streams. So if we take a list of products, and for instance, we would like to produce like product has a color property, we would like to count how many colors we have, how many products we have of each color. We would create a stream, and then we will convert the product into a color, and then we would do this like group by collect transformation. The important piece here is like you don't need to look at all the details, but the important piece is that we started with product and we ended with something entirely different. So essentially, we ended with a map of string and long. So we transformed our data. And generally, this is not a problem until you have lots of these transformations, and then you start hitting into like a couple of limitations. First limitation is kind of not as painful, is that streams don't have all the operations that you need. They don't have joins, for instance. But it's not even the main thing. The main thing is that in Java, you will still, like each intermediate step, you will need to represent some object. And very often it means you either create some meaningless classes, so at every step you would need to combine some pieces of data that don't represent anything meaningful just yet. They will represent something meaningful at the end, but you still need to name them somehow, model them somehow. Usually you don't bother with creating classes at every step, so instead you would create some kind of generic structures like maps or lists or something like that. And sometimes you would end up with this deeply nested, ugly structures. And I've done it a lot of times, and and then I'm looking at my code, and it's like, what does it mean, really? Can you really read it and understand what it means? So, looking back at all the technologies where the native data processing technologies like databases or big data frameworks like Spark and Flink and Python pandas. If you look at those, all of them represent data not as data objects but as tables. So they just create like this bigger objects that can have actually some useful behavior. And of course, the most popular language for data processing is SQL. So I'm just showing it for a comparison with this stream. And this is one of the few places where SQL is actually more readable than any other code. And the point is here that SQL actually focuses on data instead of the language syntax. So language syntax is about data. But that's a bit of an aside. So the important piece is that we are, instead of data objects, we're representing our data as tables. So why can't we do it in Java? Of course we can, but historically somehow we didn't, and we're not even looking that way. So once you start talking about tabular representation, it means that you're already working on a big data project usually. But it doesn't have to be this way. So there's nothing inherently special about tabular representations that you need Spark cluster to run it. You can run it anywhere given the right library. So and this is what we're trying to achieve here. So we're trying to create this table objects that we call DataFrame. Essentially, like in some frameworks it's called tables, in some frameworks it's called DataFrames. I prefer the term DataFrame because table is too generic, so table can mean many different things. So DataFrame specifically is just this data structure. So since there is no DataFrame in Java, a third-party library had to be created, and I started this project called dflib. I'm sorry, slide rewinding takes some effort. There's this library called dflib. It's not the only DataFrame library, but that's the ones that I'm working on myself. It's quite capable. It's open source. Its core is dependency free, so it's actually kind of like cheap to include it in your project. You're not going to get like a tree of other things. Of course, connectors to different things. They include the libraries to read those things. Like for instance, I don't know if we're reading from Parquet, so we need to bring in the Parquet library to read Parquet files. But generally, the core is dependency free, so you only have the things that you need. Its central object is DataFrame. So essentially, this one object you need to learn from this library, DataFrame, and everything else is operations on this object really. Another good thing, so in addition to a DataFrame, so DataFrame is kind of this missing component. When I started the presentation about it, like why is Java not used for data processing? It's because it's missing that piece. But along the way, I'm going to show a couple more tools that are useful. In your toolkit, when you're working with data, they are not required. You don't have to use them, but they're very nice, and I'm going to do a demo using this environment. And here I'm talking about a developer notebook. And developer notebooks, of course, they're very common in any data processing environments. And if you work with Spark, or if you're a data scientist, or if you're working with AI models, you're very likely using Jupyter. So Jupyter is like one of the notebooks. The way it is written, it supports Python and a bunch of different languages, but it can also support Java, and that's another unknown that people kind of like not aware of. So when they talk about Jupyter, they usually talk about like Python. Usually. So it supports pluggable kernels. So essentially, somebody created a kernel for Java, and then they abandoned that project, and we took it over and we brought it to dflib, and we started supporting it. We fixed all the bugs, and there were lots of people who were just opened those bug reports, and we finally got to that, and now it's in a quite good shape. So it can be used with Jupyter, and then you can get this interactive environment, and you will see this environment in a second, so you will see what I'm talking about. And finally, the topic of the demo. So what the data transformations that I'm going to show. One of my biggest clients is National Hockey League in North America. So it's about ice hockey. I don't know how many people care about ice hockey in Poland. Probably some and a little bit, but definitely it's very big in US and Canada, and it's not that different, like from this sort of data transformation perspective. It's not that different really from like anything else, from football or whatever. What I'm going to show here is an example of an ETL. ETL stands for extract, transform, load. So this is usually a process when you need to get data from somewhere, do something with this data, and save it in your data store. So that's how your system acquires data. So it's usually called an ETL. ETL usually is associated with some pretty complex tools, some special services running somewhere. I'm just going to show how to do it just in straight Java, and we can do it as part of your application. And what we're going to what data we're going to be moving here is we're going to take a list of hockey games that come to us as a CSV file, and we're going to turn that into team standings. So team standings means like in what order teams are on any given day when they're playing in a tournament. So essentially team positions in a tournament on a given day. And we're going to load those standings into Postgres database. So we take a CSV, transform it, load to database. So let me go back to my computer and start Jupyter. So Jupyter is, it can run on a server, or it can run on your machine. It's kind of a client-server thing. Just type in Jupyter Lab here, and it's going to pop up my browser. And I have some, so what I'm opening is called a notebook. So it's just a file where you can interactively execute pieces of code. In our case, it's pieces of Java code. And it can be combined with some presentation pieces. So you see like each cell it's either, some markdown text, or it's a piece of code. So markdown, of course, it helps with demos, annotations, and so on. So the next cell is the only one that's not standard Java. This is kind of a Jupyter thing. I have this %maven there, and like anything that starts with % is the official term for that is magic. I know it's it's a little weird, but like in Jupyter, it's magic is essentially this directive that does something, and this particular directive it brings in dependencies dynamically into your environment. So it's kind of like it says Maven, so essentially it does something that Maven does. It brings dependency in there, but unlike Maven, you don't need like the whole POM to work with this. You can add dependencies anytime you want. So I added this couple of dependencies. I added dflib, and I added Postgres driver. And dflib already like loads some imports into your notebook by default to help you to get coding start faster. But there are a few extra imports that I need, so I'm gonna add them. And now I can start loading my data. So let me show you what the data is. So here is that CSV file. It's just a list of games, so it's not interesting by itself. It's just the fact that this is a CSV that somebody sent us. That is a snapshot of something, of the state of the championship on the current date. So what we're going to do first, it's all about data frames. So we're going to create a data frame. And we're going to do it with, you see in Jupyter there's some like auto suggest capabilities. They're not as advanced as IntelliJ IDEA, but at least it still helps you to figure out what APIs are available. So we have the CSV class with static methods to load CSV files. And hopefully I remember the path correctly. CSV. And Jupyter, each Jupyter cell, it prints the output of the last command. Assignment is not considered like an output or anything, so it's not going to print anything. So to print a data frame, I need to enter this line here, and I can execute it, and we have a data frame object. So it's very simple. So I loaded CSV in just this one line of code, and it's already a data frame. So we have this wealth of operations. So we can start doing something interesting with it. Also, the output here is it's done the way that you can work with big data sets and just understand what they are instead of being overwhelmed by thousands of rows. So it does this smart truncation. So the first thing we're going to do here. So we have a list of games, and somehow we need to arrive at standings. So we're going to do it step by step, converting this from one data frame to another, to another, to another, until we finally arrive at our final state. But the first thing we're going to do is we're going to do some data exploration. We are interested only in some games. We're not interested in all games for this calculation. We're only interested in games that are finished already. And we have multiple game states here. We only see 2 here, but there's probably more that are truncated. So let's actually see what game states we have and then decide which games we will need. To do this, we can do a quick operation. Just get this column, game state, and on the column object there's a method called value counts. So it tells us the statistics of this column. So we can see that these are the game states that are found in the data set, and we can analyze it and applying some business knowledge. So I'll skip on that part. So we'll need official games off. So it means that the games are finished and there's already statistics for this game, and also final games that games are finished but statistics are still being processed, but we already have the score, so we can calculate the standings. So we need these two guys, and we create another data frame, and we're just going to filter those rows. To filter rows, there's a rows command, and here we can define the criteria for filtering, and we have in DFLib we have an expression language that allows us to create all this criteria for filtering or just data transformations and so on. Those are static imports that are already kind of included in our environment. So everything that looks like methods, those are actually static imports implicitly on the expression class. So what I'm going to do here is I'm going to pick a column, and the column is going to be game state. And now I can see what operations are available in the column. And I'm going to pick in operation, so it's kind of like SQL. So we're saying like column game state in official and in final. And then we need to call, okay, I'm missing a parenthesis. Now we need to call select to produce the result and print df2. So here it filtered a bunch of rows, and we are only left with the rows that are relevant for our calculation. All the future games were removed, so we're not gonna take them into account. We also don't care about a bunch of columns here, so just as well we can drop some columns that are not part of the calculation. For instance, game ID, date, arena, they don't have no effect on the standings. So I can do also calls, but instead of calls, I'm just going to do calls except to exclude these columns. I'm going to exclude game ID, and exclude date, exclude arena, and actually also exclude game state because it's no longer relevant. And we already have selected the end, so both operations are going to run simultaneously, and I rerun it again. So this is the beauty of Jupyter. I don't need to recompile or anything, so I just rerun this little cell. So now we have just the columns that we need, team scores and the overtime status of the game, and we can continue with our calculation. So the next thing we need to do is we need to split the game. Game information contains the info about two teams, right? The home team and the away team. To calculate statistics for a given team, we need to actually have just one team in a row. So we need to split this in two parts. So essentially each game will produce two rows, one per team, and then combine them together in a single data frame. So we are going from data frame to data frame. And this is a little... Okay, let me actually steal some code from here so that we'll save on some typing. So I already have it done in a different notebook, so I'm going to steal it from another notebook. What I'm doing here is the same columns operation, but I'm defining just the common columns that are not relative to, whether that's a home game or that's an away game. And in the first data frame, I'm going to put the away team as the main team, and in the second data frame, same columns, but I'm going to put home team in there. And then I'm gonna glue them together, so it's kind of like a union in SQL with this vconcat operation, so vertical concatenation, because you can concatenate data frames vertically or horizontally. So here is another resulting data frame that's it has twice as many rows, but at least everything is per team. So now we can start calculating the statistics for each team. And what we want to do, let me show you the what we want to arrive at. Okay. So this is our table in the database that we want to populate. So it has, as you see, it has a team, it has points. We haven't discussed what the points are, how they're calculated. We're going to get to that in a second. It has goal differential, which is the difference between how many goals the team scored versus how many goals were scored against the team. Again, it's no different between hockey, football, or many other sports. games played, so how many games were played so far by a given team, and finally the rank. So the rank is our standings. That's how the teams should be ordered. So we're gonna calculate those columns, one by one, and we'll finally arrive at this structure. So the first thing I want to do is let me calculate, for instance, goal differential. That's the simplest one. So goal differential is just score minus opposing score. So I'm gonna do again calls, and I'm gonna call it goals diff. Which goal diff probably. And then instead of select, since I don't like here, so far we did we picked some columns and then we did select. So essentially it threw away all the other columns. It only returned our columns. Here we want to keep expanding our data frame. So with this data frame, we're just going to add more columns. So instead of select, I'm going to do merge. So it will calculate a new column and will merge it into the data frame. Here I will provide an expression to calculate this goal differential. How do we do it? We do a column score, but unfortunately these columns, they came from CSV. So essentially in CSV everything is a string. There's no schema. So we need to convert it to an integer first, cast as integer, and then we can have all these arithmetic operations on integers. And we do the same thing with the opposing score. Also cast as int. Okay, and let's print df4. You see we have like another column. The original data frame got preserved, but so we have another column. So it's very easy to just expand, shrink, add columns, remove, recalculate things. So the second thing we're going to do is we'll need overtime for points calculation. I'll explain in a second. But for overtime to be useful for us, we need to just clean up this data a little bit. So you see here we have empty strings. Those are not null. Those are empty strings. We also have something called SO. We also have something called OT. So a bit of explanation on how it works in hockey. And this is how we calculate the points. If a team wins a game, they get 2 points. If a team loses a game in like regulation time, so essentially in the normal game time, they get 0 points. So 2 or 0. But what happens if they have the same number of goals at the end of the regulation time? It's a tie, but NHL doesn't allow ties, so somebody has to win. So they keep playing. They go into overtime, and in the overtime period, if somebody scores, they won. And those who won, they got 2 points, but those who lost, they get 1 point, because they persevered till the overtime. So essentially, they are awarded an extra point. So this is why overtime is important. Then the last question I want to answer here is like, what is SO? So SO stands for shootout. So if by the end of overtime there's still a tie, so nobody won, the game goes into shootout. It's like in football, they're doing like penalty shots. Essentially, it's the same thing. Like when it's like 1-on-1, a skater goes against the goalie and tries to score, and they're doing it in series until somebody wins. So shootout actually like is the final thing for someone to win. But from the scoring perspective, it's the same as overtime. So it's just 1 point if you lost and 2 points if you won. So we need to normalize that and just turn this like strings into just true and false. And I can do it right here actually, because we can do multiple column operations at once. So instead of adding a new column, I'm gonna override the overtime column, because merge here. Here we're gonna do an overtime column transformation, and we'll save it back into overtime column. So I do column overtime, and there's no standard expression for just checking for blanks. So instead I'm going to do just a lambda, like a custom function essentially. I do map value, and here actually let me make it a little better. So it's a string, so it will give me more options. So I won't need to do a cast here. So here I can just pass a lambda that does something to a string. And so here we want to do is s is not blank. So hopefully this will do it. Yep, so essentially that column just turned into a bunch of true and false. This will help us with points calculation. So now we're finally ready to do points calculation, and this I'm probably also gonna copy paste just to save some time. So we add another column points. We're also doing the merge, and the expression here is a little more involved. So what it does, it's also there's an if expression, kind of like an SQL, like inline if expressions, where the first argument is a condition, and the condition is the goal differential is greater than 0. So if it's greater than 0, then you won. If you won, you get 2 points, and if you lost, then we check for overtime. So another if. And if you lost in overtime, then you get 1 point. If you lost in regulation, you get 0. So we execute this, we get points. So we get another column here, points. So I think we have enough stuff to actually start doing aggregation. So right now we have all this information is done per game. So each row it represents a game for a given team. So now we need to aggregate the entire season. So it's kind of like an SQL group by with having. In DataFrame is actually very close to SQL logically, even though the syntax is not, it may or may not be like SQL. So for aggregation, so first of all we need another DataFrame, df6. We do df5 group. So we want to group by team because all the statistics are per team. We can specify the columns we want to see in the aggregated result, and those are the columns from here, except for rank. So this is the first 4 columns from here. So we assign them these names: team, points, goal differential, and games played. So we haven't seen games played yet. We're going to calculate it during aggregation. And now we can do, it's not call, it's calls. And now for each one of these columns, we need to provide an expression that will calculate this column. And so for the team, expression is very simple. It's just call team. Since we are grouping by team, so these expressions are applied per group, and then they're combined into a DataFrame. So essentially, since all teams in the same group are the same, we can just pick one. There's a method called first. So we just pick the first team from the list of similar or identical teams. For points, we need to create a sum. So here we need to cast it to integer from the start, and or rather read it as integer. We do sum. Same for goal diff. So we do int we do a sum. And finally, games played. So we don't have a column to combine to do games played, but it's simply a number of rows in a group. So we can just apply a function without this count function that doesn't take a column. So see here, we instead of 1500 rows, we ended up with 32 rows, and this is our this is all this information that we need in standings, but we also need to calculate rank, and to calculate the rank we need to sort it properly. So how do you sort data frames? Let's actually reuse the same df6 data frame. There's a method called sort, so you can of course sort it, also specifying some expressions. So let's start by sorting it by points, and we sort them in descending order, because the more points you have, the higher the rank. So so we just ordered everything, but as you can see, some teams they have the same number of points. So we need more sorting criteria. So we need to resolve. We need to decide who is better than when they have the same number of points. And for this, we're going to use our games played that we just calculated. So the fewer games you played, the more chances you have to score more points. So you scored the same amount of points in fewer games, in other words. So here you can also sort on games played in ascending order. So fewer games, you're placed higher. And finally, if there's the same number of games and the same number of points, then the third criteria is used is goal differential. a goal differential, and it's also descending. So essentially, the higher the differential, the higher you placed. Okay, so we calculated this, and finally we need to add our rank column, so that our consumers don't need to sort it every time. So they will always have this canonical value of standings, and that's just another column. That's a data frame. So essentially, adding the property is just adding the column, and the column is called the rank. I want to do merge, and the expression is actually very simple. It's a special expression called the row number. So here's our rank. So this is a standing. So we did in our ETL process. So E standard for extract. So extract, that's when we read our CSV. Transform stands for T stands for transform. So everything we did here, it was a transform. Now we're finally at the load phase when we need to load that to the database. Data frames, again, they're very versatile, like unlike ORM, where it's tied to the database that you kind of started with. You model that database, you only can work with this database. You can read and write data from the database. Data frame is it's just like a list or a map. It's not tied to a data store, so you can read it from any data store, you can write it to any data store. We're going to write it to Postgres. That's just a little more involved than working with CSV. We need to define this connector object. The object itself is not interesting, so it doesn't print anything meaningful. And now with the connector, we can actually do some operations. Because data frames, they look just like tables. They actually map one-to-one, so that the column names and data frame, they map to column names in database tables, so it's very easy to save it. You don't need to model it or write SQL or do anything like that. So you can do, we have an object called table saver, and the table is called standings. Also, it means that today I can save to this table, tomorrow I can save to some other table. And just do save df6. So when executed, SQL is generated by the framework. Here we have some stats. So it's 32 rows. That's how many teams there are in the NHL right now. And if I go to the database, the result of a select will be expected. So it's just those 32 teams ranked according to their current position, in the championship. So we already have a naive kind of ETL transformation. So we can take a CSV, we can load this data to the database. In the real world, what are we missing still? We are missing the fact that the CSV is going to arrive multiple times, every time with different data. So we need to update this data over and over and over again. And we can actually emulate this real quick here. Like say, for instance, we have Vancouver in the second place, and let's go to Van and do something bad, like a game they won. Let's just fudge the data as if they lost the game. So I just changed the score, flipped between Edmonton and Vancouver in the CSV manually. And now I can go and load it again. Again, the beauty of Jupyter, I can start at any place in the notebook. So I'm going to recalculate this. You see Vancouver got pushed to the 5th position because we changed the data. Okay, so now when we want to save it, if I save it again, it's going to insert another 32 rows, which is probably not what we want, because the standings is kind of a snapshot in time, so it shows like where the teams are. It shouldn't contain the same team more than once. Many organizations, even like pretty big ones, I've seen they're doing this type of tasks. They're doing something pretty ugly. They would do like a delete from the source table, and then they will reinsert. So essentially, like every time they update the data, they wipe the table clean. And imagine, for instance, if you have something like Debezium or whatever, you're receiving events from the database, and suddenly, like, you have this like huge batch operation just to update a couple of things. Of course, we want to be smarter, and instead of just saving it, we're gonna merge the data in a smart way so that only the things that are updated in the database. And for this, we have a method merge by either by primary key or merge by columns. Let's actually merge by the team column. So it's gonna compare what information is available for this team already in the database, and try to generate something smart. So here you see it's instead of inserting, it did 6 updates and 26 rows were unchanged. And to do this, it did a select first. So it selected internally. It's all transparent to us, but internally it did a select from the database, created another data frame, took our data frame, compared the two, and compared, I mean, like did a full join essentially. So did a join of 2 data frames on this team column, and essentially detected the changes and generated a proper update SQL. So that's the end of the ETL transformation. So this code can now be copy pasted into your job, into your Java application, and you can run it, on Amazon or anywhere you want. I wanted to show something else that's not related actually to stand-ins, but it's kind of nice. And I think that's another missing piece in Java as far as data processing goes, and I'm talking about charts. So I'm talking about data visualization. I worked with Java since late 90s, so I still remember when people were writing stuff like Java applets, and there were some popular frameworks for charting in Java, but somehow when Java just moved to the backend, people forgot about those, and there are a few open source solutions, but they're really behind the curve, I think. For instance, if you compare with what people have in JavaScript, like for instance Apache charts. I wanna show where the state of the art is. So this is amazing essentially, and we don't have this in Java. And here it's I don't know why it's not scrolling in Firefox, but you have all this dozens of different types of charts. You can even chart a cow. I don't know. The thing is, how do you make this available in Java without rewriting everything? So I creating alternative solutions for some popular solutions where we can do some things better and so on. But in this case, I was no, not this one. So what we did in DFlib, we created actually Java APIs that generates this JavaScript just. If you're in Jupyter, it just renders it right there. If you're not in Jupyter, if you're some kind of backend service, you can still serve this JavaScript as a resource to the front end and display this chart. So let me show you how this works. So we have this class eCharts that's sort of a factory of all charts. We create a chart, and here we don't have much meaningful data to chart, but we can still chart something. We can, for instance, do a bar chart of points by team. So on the x-axis, we're gonna put team. So I'm just referencing the columns in DataFrame. And DataFrames are very, the correspondence between the chart and the DataFrame is very direct. So it's very easy to model a chart. And for the data series, we're gonna pass. So here we need to specify the type of series, and there's going to be a bar chart, and you see we have a bunch of options. And we're going to pass a column, points column. And here we're going to call plot on our df6, the last data frame. I'm going to execute it, just a couple of lines of code. So once you have a data frame, just visualizing it, it shouldn't be hard. And with a few tricks and with this sort of wrapping of this amazing JavaScript API, we can do this. And let me show other chart types maybe. So maybe instead of points, let's do goal diff. And instead of bar, let's do line. So we have this again. I don't need to think about access too much. Just bind some data. Of course, there are options to visualize make everything different color, or create some tooltips and actually mouse over behavior. But the basic chart is just this. I mean, this is the code. This is it, and we can actually combine the two if we want to. So we can have both on the same chart. So I think it's pretty neat, but it's also in addition to just being something that Java developers already forgot how to do. It's also great when you're working with data. So you suddenly you're a Java developer and you become a data scientist. So when you get in a CSV from your some upstream system or some business users or whatever, you can actually analyze it here before you start writing your code. So that's really cool, and being able to visualize data is invaluable, really. Okay, so enough with the demo. Let's go back to the slides. The rest of the presentation is going to be about, okay, so what is the use cases? So this is all great, but should we just throw everything out that we are using daily and just instead of objects start using data frames? Certainly not. So the idea, so on this slide is I'm trying to demonstrate the cases where you don't use a data frame, where the current other tools are much more appropriate. For instance, if you have this CRUD situation where you don't change the data structure, where you're not doing transformation, where you're just reading objects from the database, you're saving them there, just keep using the ORM. When you're doing simple transforms, again, you probably don't need a data frame library. You can have like a few objects, and even that examples that I had on the slide, doesn't need a data frame. Another example where you may have a lot of data, but it's already in the same database. Please don't read it to Java just to save it, do something and then save it back. So just if you could do it with SQL, do it with SQL. Respect data locality, because it's going to be much faster and use fewer resources. And finally, when the data set is very big, so data frame is just like a map or a list. If it fits in memory, it works. If it doesn't fit in memory, it doesn't. So essentially, if your data set is huge and it's not easily partitioned, then you're entering the big data world. You keep using Spark, Flink, whatever is appropriate, and this is fine. And they have their own data frame. So essentially, you will be using the same data frame just in their environment, which is a little harder to deal with, but it gives you all the power. So when do you use a data frame? When the data fits in memory, and we actually this is becoming a little vague because we're talking about like using memory mapped files and everything. It's like in the new versions of DFLE, we're going to expand the definition, essentially what is memory. Then when you have some transformations in your code and you're seeing this like deeply nested data structures in your streams, probably means that your data is already, like, transformation is complex enough that you probably should try a data frame. The next point is you keep re-implementing joins and group by, and this happens just inadvertently. You may not even think about it, but like, for instance, if you like read one stream into a map and then you start another stream, and when you process in that other stream, you look up objects in that map to compare with your current object in the stream. Congratulations, you just implemented your own join algorithm. So probably, I mean, it's not rocket science, it's not hard, but probably shouldn't be doing that. If your data sources are already tabular, data frame is a good fit. If somebody has uploaded in Excel through your interface, you probably should try using a data frame instead of using like low-level stuff like Apache POE or whatever. So this is what we are using to produce a data frame, but you want this structure. You don't want like the formatting of that file. Usually, you usually want the data. Mix of data sources. That's another example where, for instance, like ORM, like I mentioned, it works narrowly with a single database that you modeled. It can't work with anything. With data frame, you can get one piece of data from CSV, another from Excel, joins them together, and saves them to database or saves them to JSON. So it's really flexible. Some examples is data exploration. So this is where the charts work real well, and so understanding what's in a data set even before we started coding against the data set. I use it a lot for ad hoc log analysis. So like from a log system, I just request via the REST API some time series data for a period of time, and then I can actually do some checks on like how well my application performs, and then drill down if it doesn't, like what happens within a single request, for instance, and stuff like that. I already mentioned Excel uploads, and the last point is like no drama ETL. We've seen that in the demo, but why do I call it no drama? Because usually ETL systems, they can get pretty complex. There are whole like multi-billion-dollar companies that provide ETL tools, and you bet you need to like some learning curve, like Talent, for instance, or something like that, where you actually need to install it, learn it, deploy it in a certain way. Here, if your use case is simple, just whip up a data frame and just put it in your Java application and deploy it together with the rest of your service, for instance. So the conclusion here is the data frame is a Swiss Army knife of data processing. It's really flexible. It's not, the structure is not fixed, so you can do really any data transformations with it. It doesn't require any special infrastructure like big data frames like Spark or Flink, where you start by buying something from Amazon essentially. It is very similar logically to SQL, but unlike SQL, it's more composable. So you can actually do these transformations one by one and look at the result, as opposed to SQL, where, well, I guess you can also like copy paste pieces, but it's not easy to like take a big SQL query and see what happens in the middle, with lots of like subqueries, unions, and so on. It's not a replacement of anything, but it has its own niche. And if you understand that niche, you will find it in your use cases, and it will hopefully help you to solve your data problems in a more efficient way. And the final touch is notebooks and charts. They're not required for anything that you do, but it is another tool in your toolkit that you can use to your advantage, essentially. So you can have this really dynamic environment to figure out how to work with a data set, and you can actually visualize your data. So that's the presentation. A couple of links to the tools that I mentioned here: DFlib, Jupyter itself, and DFlib JJava Jupyter kernel. So all the documentation how to install like Jupyter, for instance, Jupyter and Java is in this JJava link. I appreciate if you like what you've seen. I mean, we're an open source project, so we live off of our reputation. So if you can give us a star on GitHub, but only if you like it. Thank you.